this video, we're going to briefly overview the idea of mass energy equivalence. We'll take another quick look at binding energy, and then we'll compare binding energy, the energy released in certain reactions, to other types of energy that are released in other reactions. So we're going to take a more comprehensive look at how mass is lost during reactions and how this produces a release of energy into the environment. Then at the end, we'll overview the differences between radioactive decay, fission, fusion, natural transmutation, and artificial transmutation. So, we know that mass and energy are equivalent. Einstein famously said this with the equation that E, energy, is equal to mass times the speed of light squared. So if an object gains energy, then it gains mass because of the equivalence. If an object loses energy, it loses mass. And vice versa. A loss of mass means energy is lost. And a gain of mass means that there's a gain of energy of the system. So there's an interesting question here, which is how much energy exactly are we talking about as being stored in mass? So for example, how much energy is stored in one atomic mass unit? Another way to discuss or ask the question is, what is the energy equivalent of one atomic mass unit, or 1U? So we start with the equation E equals mc squared, and then we are going to plug in or substitute in for mass 1U. The speed of light, we can use a pretty precise value, 2.998 times 10 to the 8 meters per second, and we square it. Now this atomic mass unit, we need to convert to kilograms first, so we use a conversion factor, and we have our speed of light. And when we calculate this out, we get 1.492 times 10 to the negative 10 joules. And we can take this value and we can convert it into electron volts because of how small it is. Okay, so electron volts is a more appropriate value or unit to use when expressing such a small amount of energy. And when we do, we get approximately 931.5 times 10 to the 6 electron volts, or we get 931.5 mega electron volts. So we have our equation, right? E equals mc squared, and we just said that 931.5 mega electron volts is equal to 1U times c squared. So one atomic mass unit is really no different. Well, if we divide both sides by c squared, then 1U is equal to 931.5 MeV over c squared. Or 1U is 931.5 MeV times c to the negative 2. So we can use this MeV times c to the negative 2 as a unit of mass when discussing nucleons, right? Because and when we do, it's very, very easy to convert that given mass with units of MeV times c to the negative 2. It's really easy to convert that to an energy. You just drop off the c to the negative 2. Get rid of it, and now you have the energy equivalent. Okay. So we can go back and forth. Another way to think about this is we can go back and forth between a U, an atomic mass unit, and this many MeV. And that's how we get back and forth between energy and mass without having to multiply every time by c squared, and without having to convert, like I just showed you, from U to kilograms and then from joules to MeV. So this is a way of avoiding the whole process we just saw. Now, whenever a system loses mass, the system loses energy, which is released into the environment. So if we have a negative mass delta M, mass loss, if we have mass lost, then we have a release, positive energy, into the environment. So we've seen many types of reactions where mass is lost and energy is released from the system into the environment. Right? Here's one example. If we take a bunch of free nucleons and we combine them to form a nucleus, mass is lost and energy is released. Other examples where mass is lost are radioactive decay. And then we also saw fission and fusion. And all of these energy is released and there is a loss of mass during the reaction. So here is the first that we're going to look at, the formation of a nucleus. If you take 88 protons and you combine 134 neutrons, you slam them together at a really high speed, you'll produce thorium-222. And if you compare masses, the left side, the mass of the parts individually, when they're not bound together, when they're free, the combined mass is bigger than the mass of the whole thing, the nucleus, which means that there is a loss of mass. We have mass loss during this reaction. That means energy is released into the environment. Because there is a loss of mass, there's a loss of energy, which must go somewhere. It's released into the environment. So we add energy into the environment during this reaction. Now, this energy which is released into the environment when a nucleus is produced is given a special name called the binding energy. And the amount of mass that's lost in this special case, the formation of a nucleus, is called the mass defect, or sometimes the mass deficit. Alpha decay. Here's an example of alpha decay. If we compare the masses, the parent has more mass than the alpha plus the daughter. That means we are losing mass. Mass is lost. And if we lose mass, then the system loses energy, and that energy is released as positive energy into the environment. Beta decay. Here's the example of beta decay. We can also write beta decay as a single proton changing into a neutron while emitting an electron, a beta particle, and an antineutrino. So this is another way to write beta decay. So if we compare masses, we see the left side, the parent, has more mass than the right side combined. Mass is being lost during this reaction. That means the system loses energy because it loses mass, and the energy is released into the environment. So we have positive energy being released to the environment. The next is gamma decay. Notice that the nucleus, the parent nucleus, doesn't change elements. But we still have, nonetheless, we still have smaller mass at the end. So mass is lost, which means the system is losing mass and losing energy. That energy is given off as positive energy to the environment. So the next example is fission. Now here's an example of a fission reaction. If we compare, the left side has more mass than the right. That means that mass is being lost. Mass is being lost. And if mass is lost by the system, then the system loses energy, which means the system is emitting positive energy into the environment. Fusion is another example. If we compare the sides, we get more mass on the left when we add these masses than on the right. Now, mass is lost in all of these. Mass is lost, and we release energy because the system loses energy to the environment. Energy is given to the environment. Now, in fission, a bigger nucleus always splits into two or more smaller nuclei. But there are important requirements for fission beyond just this. There have to be at least two or more roughly equally sized daughter nuclei that are produced. So the daughter nuclei have to have masses that are approximately, 1 to 3 or 2 to 3 or 1 to 1, some kind of relatively close ratio. Additionally, one or more neutrons have to be produced for the reaction to require fission, as understood by the IB. So here's an example of a reaction where there's an alpha particle being shot off. This is alpha decay. Why isn't this fission? Well, for one, the two daughters have way different masses, nowhere near equal, right? Not even 2 to 3 or 1 to 3. And for another, there are no neutrons being produced on the right side of the equation. So here's an example of a fission reaction. We have two daughters, which are roughly equal, 2 to 3 as the ratio between the two, between these two masses, 89 and 144, roughly equal. And we have some neutrons being produced at the end. So this does qualify as fission. Now, transmutation, here's the definition. It's the process of a parent nucleus changing into a different nuclide or element. And this occurs when one or more nuclei nucleons are either emitted or absorbed by the parent. Natural transmutation is what you get when the transmutation that occurs is spontaneous. That means that only the parent is on the left side of the reaction. Only one thing is on the left side of the reaction. So this example right here, a fission, is not a natural transmutation. There is a transmutation occurring because the uranium changes into two different daughters, two different elements. But it's not natural because we have another thing on the left besides just the parent. In natural transmutations, we always have a release of energy. Radioactive decay is the process of an unstable nucleus losing energy and mass, should we say losing energy and mass, by spontaneously emitting ionizing radiation or ionizing particles. Now, some transmutations are artificial or induced, and that means that they occur when the reactant, when the parent nuclide, collides with something else, or when it absorbs radiation. With everything that we've seen so far, every example, there has been a loss of mass during the reaction, which means there's a release of energy into the environment. Energy is being released or produced and given off into the environment. With these artificial or induced reactions, sometimes energy is released, like we just discussed, but other times energy is absorbed from the outside environment. So we've seen that in order for an object to lose mass, it has to release positive energy into the environment. And as it turns out, for a system to gain mass, to have a positive delta M, right, then the system must absorb energy from the environment. So that means energy is being sucked out of the environment. That's negative energy, right? The opposite of energy release, the opposite of positive. So here's an example of that. If you take mercury and you collide it with a neutron, then you can produce gold and a hydrogen atom. Now, in this reaction, if you compare the left and the right masses, the initial mass, right, the mercury plus the neutron, has less mass than the gold plus the hydrogen. So when this reaction occurs, there's an increase of mass in our system. There's an increase of mass, which means that there is energy being absorbed into the system, and there's an energy loss from the environment. So rather than giving off positive energy into the environment, we have negative energy, which is being absorbed from the environment, and that's what this means here. So we saw an example, a problem, where we had to subtract energy from the right side because the final energy was bigger than the left side, the initial energy. I'm sorry, the final mass was bigger than the left mass, the initial mass.